In the previous lesson, we talked about our thinking about the atom up to John Dalton, who in the early 1800s formulated the first scientifically backed model or theory of the atom. Well, some 60 years later, we meet William Crookes, who played a very, very tiny role in pushing the atom further. So let's talk about what Crookes did. He used what he called a Crookes tube, or a gas discharge tube, that is a container that has had almost all of the air evacuated from it, and he hooked it up to an electric potential difference, and what he found was that rays causing a shadow were emitted from the cathode on this gas discharge tube. The cathode was this portion right here, the anode was down there, and it so happened that Crookes had this Maltese cross shape as a piece of metal inside the tube, and what happened was there was a shadow produced on the back wall, you might say, the back surface of this gas discharge tube, just like you would get a shadow if you were to shine a flashlight at this Maltese cross, and it had a nice Maltese cross looking shape. Crookes didn't know what they were, but they came from the cathode, so he called them cathode rays, kind of like sun rays. It turns out that old school computer monitors and old school televisions and old school radar screens used what we now call cathode ray tubes, which were essentially this exact technology. Well, some years later, J.J. Thomson, who was British, discovered that cathode rays are deflected by electric and magnetic fields. In other words, if this is a gas discharge tube, let's say on the right here we have a screen that's coated with a chemical that will glow when it's hit by radiation. And over here, we're going to project some cathode rays onto that screen, and so we get a spot on the screen that glows. Well, JJ said, well, I wonder if I take an electric potential difference and put it around that discharge tube, and then I shine my cathode rays, I wonder what happens. Well, here's what happened. That cathode ray deflected. Now, if they were just rays of light aren't affected by magnetic fields, and it would just go straight. So, JJ figured out that these aren't rays like light, they're actually particles. And based on the way they deflected, he figured out the charge on those particles. You can see here that those particles, as they're going to the right here, are kind of pulled towards the positive and pushed away from the negative plate. Well, what would be the charge on a particle that tends to veer toward positive and away from negative? Well, that would be a negatively charged particle, and today we call them electrons. So J.J. Thomson is credited with discovering electrons. And since the atom was known to be electrically neutral, Thomson proposed the plum pudding model. In other words, Thomson figured out that there were negatively charged particles, therefore there also must be positively charged stuff. And it was also found, I won't go into how, that the positive stuff was like way more massive than the negative stuff. And so Thomson proposed his plum pudding model, which is little electrons embedded in a much larger positive, mushy, squishy type mass, where the amount of positive and the amount of negative charge is equal, although the mass of the positive stuff and the mass of the negative stuff were found to not be equal. Thomson called this his plum pudding model. If we were naming this. From an American point of view, we might call this a raisin or a blueberry muffin model, or a raisin nut banana bread model, where most of the dough is of one thing and then there are little bits of something else embedded within. Thomson formulated his plum pudding model in the early 1900s, and there were some significant findings about the atom that took place shortly thereafter, but I want to skip ahead about 30 years since we're talking about subatomic particles. Thomson discovered the electron, and therefore he also discovered that there was positive stuff in the atom. Neutrons weren't discovered until 30 years later or so, despite the intense scientific work that was being done on the atom at the time. And that's because neutrons have no charge, and therefore they're difficult to detect. They don't respond to electric fields or magnetic fields. So, despite scientific effort, it took quite a while to figure out that, hey, there were these things called neutrons. We know now that the purpose of neutrons is related to making the nucleus of the atom stable or not. If the mix of protons and neutrons is right in an atom, then the nucleus is stable. If we have too many neutrons or not enough neutrons, then that's an unstable or radioactive nucleus. And today, we've learned about many other types of subatomic particles: quarks, positrons, neutrinos, many other things, but we're not going to go into that here. Let's summarize Thomson and subatomic particles. 1. The Greeks and Dalton had no conception that there might exist particles that are smaller than the atom, subatomic particles. After J.J. Thomson found evidence of the existence of discrete negative particles, today we call them electrons, he proposed his plum pudding model: tiny negative masses embedded in a much larger mass of positive dough. 2. Although scientific progress was quite rapid in the early 20th century, it took decades for scientists to discover the particles we now call neutrons because they aren't affected by electric or magnetic fields. Chadwick is credited with discovering neutrons.